All right, okay, it's 1 o'clock, time to get started. Welcome, everyone. Welcome back to our tutorial for historical syntax. And today we are going to have the first of 3 sessions on how to analyze our data. I invited a few people along for this. This is why I'm doing this on Zoom as well. And this is Rui over here, who is a PhD student who I'm co-supervising. So maybe these guys get something out of our discussion as well. Yeah, so this is probably the most challenging part of this tutorial, the practical side for how to analyze our data. But first, let me remind you of what we're trying to do, and this might also help Rui or the people on Zoom understand what this is all about. So we have read some literature. We developed an interesting research question. We collected all the data, we corrected the data, and it would then be time in the next step to analyze it. What we want to do is find out if the vernacular is the engine of change. This is sort of the research question that we all decided on. And in order to do this, we collected 4 million words of late medieval English. Here I say roughly 1375 to 1600, but you can formulate this differently in your paper. And we divided these texts into 2 different genre types: learned texts, that's a higher register, and texts that are written for lay people. And we are hoping that this would target more vernacular texts. So for instance, philosophical treatises or medical texts or instructions, those are learned texts. Poetry and romances and other fictional texts or saints' lives, those are hopefully closer to the spoken word, they're more vernacular texts. Then we have a specific linguistic phenomenon that we're interested in, namely, of course, the decline in dative experiences, which is sort of the overarching topic, I suppose, for much of this course. So we study the change that goes from me liked the book towards I liked the book, where me is the experiencer here in the dative, or in an object mark case, and it then turns into nominative subjects. I like the case nominative. So that's our general research question. We derive from this a more specific, quantitatively testable prediction, and it goes something like this. This is my formulation. If changes like the loss of dative experiences emerge from below, and here's the literature that I asked you to read for this, so above 2001, then the decline in dative experiences could be expected to be overall more advanced in more vernacular texts than in learned texts, even though the overall decline should be measurable in both registers. So both in learned and in lay people texts, you would expect a decline in dative experiences, but this process might be more advanced in vernacular text. And if this is true, then we have some evidence, some limited evidence, to suggest that linguistic changes tend to occur in vernacular registers first. The question is, how can we answer questions like this? Obviously, it's one thing to understand it and to have some general concept about it, and another thing to actually target it quantitatively and statistically. And for this, and for many similar predictions like this, we can use a technique called logistic regression. Okay, so this is what I will be trying to explain to you today and in the subsequent 2 sessions. This is not easy, so make sure you can come if possible. And also try to pay close attention, ask questions if there's anything you don't understand. Now, there will be a little bit of math in it, and sometimes we find it very scary because you're linguists, you like language, you don't like math, and I get this, okay? I'll be very careful, very gentle, very slow. You just have to follow what I'm saying, okay? Just don't be scared. I take you by the hand and lead you through this very slowly, very carefully. You just have to have an open mind, be alert, okay? Pay attention. Don't drift off and just do the steps and also the homework as I tell you to, and then you should be perfectly fine. It is not difficult. I boil it down exactly to those steps, like an algorithmic procedure that you need for your papers. Like you, Rui, or maybe people on Zoom, you would have to adjust this quite a bit to target to your research, if at all, if it's relevant at all. But for you guys here in class, I will tell you exactly what to do, right? You just have to follow these steps more or less like a robot. But of course, it would be nice if you understood the technique in general so that you can then apply it to different linguistic changes or even to different studies altogether. Does that make sense? Are you guys ready? Okay, so today we're going to cover the first 4 steps. The first step is basically the big picture. I want to just tell you in general what we're trying to do and what logistic regression is, okay? So what is regression? It's probably the best step to understand what logistic regression is as a specific subtype. And it's not very difficult. Regression means you try to find a model that models a dependent variable, which I will always label y and highlight in red, from some predictors, from independent variables, which I highlight in green and mark as x. That's kind of common. So you often see y as the outcome, as your dependent variable, and the x, everything that you put into the model to predict the outcome. For us, this x ultimately is going to be two x's, one for learned versus lay people texts, one for year, for time. So we want to predict the proportion of dative experiences from time, from when a text was written, and from its genre. But this x, as you can see, can be anything else, any linguistic or extra-linguistic factor that you're interested in for your studies. In practice, that simply means that we have a data cloud on an x-axis and a y-axis, and what we're trying to do is fit a line through it. It's as simple as this. This is regression, just putting a line through a cloud of data points, and this line that goes through your cloud of data points, that's what, you know, impressively is called a model. I mean, it's not really, it's just a line if you think about it, but we can call it a model. So for instance, here you see this little made up graph with some values on the x-axis and some values on the y-axis, and you want to find a good model that sort of captures the tendency. So maybe you could just put in a line, for instance, in this particular model, yeah? So this line going through a data cloud, that's a regression, and the model is just this line, and this line then tells you the relationship between x and y. And so if I give you a particular x value, the model will give you the best output for the y value. If I give you a year of composition, the model will give you the best proportion of dative experiences, for instance. Now, logistic regression is a specific kind of regression where we don't just fit a line through it. Instead, we fit a different sort of shape through our data cloud that is very convenient or very appropriate for language change. And that is an S-shape, an S-shaped curve. So imagine, once again, we have lots of data points, and we want to put a model through these data points, but we don't fit a line through it, we put an S-shape through it. And to illustrate why this is useful, let me give you a couple of examples. This is one from the lecture we looked at. That's the decline in be as a perfect auxiliary. So the change from he is come to he has come, or he is fallen to he has fallen. And when you look at this data, yeah, you can see that a good model to put through this would be sort of an S-shaped curve, wouldn't it? That's a much better model than just a line through this. You would agree? Or here's another example. That's the rise of do support with negation. So that's the change from I drink not wine to I do not drink wine. Does it make sense? Once again, if you look at this increase here in the 16th and 17th centuries, you wouldn't just put a line through it. Rather, you put the beginning of an S-shaped curve through it, something like this. And then as time goes on, you might see the end of this S-shaped curve here. Yeah? Does it make sense? Or here's yet a third example. That's the rise of the third person singular inflection S, as in he sings, which used to be an ETH. So F, he singeth, becomes sings. And once again, you can see this rise of the new form looks very much like an S-shaped curve. So what we want to do is put an S-shaped model through this. When we do this, when we fit an S-shaped model in regression, we call this a logistic regression. So far, so good? Okay, so I told you there's a little bit of math. Now, you don't even need to understand this bit. It's not important, but I think if there is one thing, one formula that you do want to remember, and I think it would be great if you could remember is, it's the logistic function. The logistic function is this S-shaped curve that we fit through the data. I'll show you this function repeatedly. It would be great if eventually you could just memorize it or remember it. Also, there are different formulations for it, so different kinds of stating the same thing, because, you know, in math, you can always transform bits and pieces. But I think this formulation here is the easiest one to remember. So it looks shocking. It's like, woo, that looks complicated. But let me just go through it. So here's our Y. That's our proportion of the new form, dative experiences or do support or be versus have auxiliaries and so on. And this E here is a constant, it's just a number. I think it's 2.71. So this E is just a fixed number to the power of A plus Bx divided by 1 plus E to the power of A plus Bx. So this is the one line of math, if you will, the one function that I would like you to remember, okay? So it's y is e to the power of a plus bx divided by 1 plus e to the power of a plus bx. Okay, so what we see here is our x, that's all the independent variables that we put into the model. So for today, that's just going to be a year number, the time. And here we see these two numbers, a and b comes right before x, which means b is sort of going to modify or give the strength of, or the effect size of x of time. But I'll explain this in greater detail soon. So try to look at this formula here and try to remember it so that it doesn't scare you. It's just this one line that I would like you to remember. So this y here, this output, can range from 0 to 1. It can go from 0 to 1 if you use this formula, which is why we use it. It can either be 0% or 100%. It could be, say, 70% dative experiences, or 25% dative experiences, or 0% dative experience. This formula conveniently constrains the output y to the range from 0 to 1, or from 0% to 100%, which is the same thing. That's very nice for us, isn't it? Because when we measure a proportion in our texts, it can either be 0% dative experiences, or it can be up to 100% dative experiences, or anything in between. Yeah, but it can't be 110% dative experiences or something like this. So that's very nice. And x, this input here in green, that can be any number. It can be absolutely anything. There are no constraints on it. And for us, it's going to be a year number. So it could be 1400, 1401, 1402, 1403, and so on. So just a real year, because every text has a year number, right? So I put in a year number here, and then I predict from this the proportion of dative experiences. Does that make sense? And the S-shaped curve will have this shape here, will have this formula. Let me just repeat it one more time so that eventually after 3 sessions it will sink in. Y, our output, the proportion of dative experiences, is e to the power of a plus bx divided by 1 plus e to the power of a plus bx. Okay. So to highlight this one more time, we have this S-shaped curve here. The y value will be on the y-axis here, and it will go from 0 to 1. Yeah, makes sense. And x here, that's our year variable, that's our time. So x here is going to say time eventually. And for our case study, it's going to range from roughly 1375 to 1600. But it could also range over different times if you study different syntactic changes, right? Does that make sense? Okay, now we have these two parameters here, these two numbers, a and b. Those two numbers are used to change the S-shaped curve, to put it in the right place, to give it the right shape. So how do we do this? Well, we can use a, that's this first number here, e to the power of a plus b times x, in order to move the S-shaped curve to the right time. I can move it to the left and to the right, but keep its shape exactly identical. Here, for instance, I indicate the logistic function where a is 0. And you see the midpoint for this, where the proportion of the new form is 50%, is exactly at 0. Now I change a and make it a different number. Say make it 1. Now it changes slightly to the left. Can you see this? The S-shaped curve is exactly the same. It just moves it to the left and to the right. So this first parameter, a, simply moves your S-shaped curve along the x-axis without changing its shape. Can you see this here for different examples? So if you use a in this function here, that will sort of put the S-shaped curve at the right time. Does that make sense? Is it a change that is roughly the 19th century or in the 17th century or 300 BC? This A will take care of putting the S-shaped curve in the right time in general. B is much more important for us. B, as you can see, comes right before X, that is to say right before time. So it will influence how important time is. If B is very large, time is very important and it will be a very fast change. If B is very small, time will not be very important. Maybe the development will even be flat and there will not be much of a real shape. So let me illustrate how B influences this curve. Here is the logistic function for B equals 2. 2 is quite large, isn't it? Can you see how steep the green line is? Here is it for 0.5, much flatter. So B makes this change slower. Here it is for 0.25, and once again, the shape has become even flatter. It's even less steep. Does that make sense? So B is our really important parameter, the parameter that tells you how important time is. It is the effect of time. It tells you if this is a fast change or a slow change. And this is why this is also often called the rate of change or the rate of change parameter. Okay, so B in this logistic function tells you how fast the change is. It's the rate of change. A is not so important. A simply moves the curve along the x-axis into the right time. So a larger B means it's a fast change. A slower B means there is a slower change. And if B is really, really tiny, we might even conclude there is no change at all. Are you still with me so far? So far, so good? Good. So I think that was sort of the first step. That was the first idea, telling you what logistic regression is, what the logistic function looks like, and what A and B do to change this S-shaped curve. How do you actually get A and B? Well, it's very simple. You put it into a statistics software and let it run the regression, and it automatically outputs the results A and B. So our data is stored in an Excel sheet, right? It will be once you're done with the correction of the data set. We then take this data and put it into a statistics software, and we're going to use R for this. So you should already have all installed it. Maybe you can install it too for next time if you want. And then it'll output the results, which will simply look something like this. It'll give you one value that's called intercept, and then it'll say something like estimate, and have a number. And this number is going to be A. And then depending on what you type in, like year or time or composition of the text, right? So whatever you have in your column for the year of the text, that will be your year parameter, your rate of change parameter B. And then you have your two values for the S-shaped curve. Does that make sense? The problem though is that these numbers here, in this case minus 31 and 0.025, are a bit difficult to interpret. The reason is that these numbers must be interpreted on a special scale that is on log odds, also known as logits. Okay, why is that? It's not important, you don't really need to know this, but it's an S-shaped curve, isn't it? So it'll be faster in the middle and slower at the beginning and at the end, right? So you can't really say there's a linear increase. So we need to transform this a bit so that it becomes a flat line where the increase is regular and the same for every year. But I'll talk you through this in a bit. So what's important for you to understand these two numbers here, minus 31 and 0.025, is to understand what log odds are. So that's the topic for step 2. Let's see if I can explain this. I think probabilities should be relatively clear for everybody. Probability is simply the proportion of the new linguistic form. So for instance, you could find 50% of all cases are dative experiences or nominative experiences. That's the same, I'm sure you know this, as 0.5. Yeah. Or you have 25% of all cases in our text are nominative experiences. That's the same as 0.25, right? Or we could say 99.9% of all cases are nominative experiences. That's 0.999. So far, so good? Okay, next we can take this and calculate from it the odds. Odds are basically exactly the same as probabilities, just a different way of thinking about it, namely in terms of the one form versus the other form. So you take the new linguistic form and divide it by the old linguistic form, right? So you take the new form divided by the old form, and it gives you the odds. For instance, if you have odds of 50%, then the odds are 50-50. And that's 1 to 1. That is to say the odds are 1. That's important. If the odds are 1, that means the probability is 50%. Or let's take this example here where you have 25%. 25% gives you odds as follows. You divide 25% by 75%. Yeah. And that's 0.33333. Or here 99.9%. In order to get the odds, you divide 999 by 1. So the odds are 999 to 1, or 991. Sorry, 999. Do you get this? Let's see, proportion of 74%. In order to get the odds, you would divide 74 divided by 26. And then that is 2.846, for instance. Now, the last step, very simple, is simply to take the log of this. So you don't even need to understand what logs are. They just transform these numbers. So all I do is take the log of these odds. So for instance, if I take the log of 1, that would be 0. That's maybe the one value to keep in mind. 50% corresponds to odds of 1 to 1 and odds or log odds of 0. What else do we have? 25%. 25% corresponds to log odds of minus 1.099. And 99.9%, that corresponds to log odds of 6.907. So on a log odds scale, what happens is that 50% is going to be 0. Everything smaller than 50% is going to be negative. For instance, 25% is minus 0.693. And everything larger than 50% is going to be positive. Do you understand what log odds are? Here's a quick exercise just to make sure. You find that 80% of all cases of like in 1400 occur with a dative experiencer. Okay, just an example. I don't know if that's true, but let's say in 1400, 80% of all cases are dative experiencers. What are the odds? What are the log odds? Yes, so it's 4. Can you see why? So 0.8 divided by 0.2, that's 4. And then you would just type in log of 4, and that would give you 1.382694, whatever. Yes. Okay, so why do we need this? The next slide is completely optional. You don't need to understand it or to follow it, but I think it's pretty cool. So let me just show you what happens. Here's again our logistic function. And remember, this logistic function expresses this sort of S-shaped curve. Now, I simply, and this would be just the odds of the new form as opposed to the probability. And this would just be the log odds. Observe what happens. This extremely weird looking, complicated monstrosity of a formula becomes super easy. All that's left at the end when you measure it in log odds is a plus bx. And I'm sure you all know this from math classes. This is just a line. A plus bx is just a line going through a data cloud. So if I measure the outcome not in a proportion, but in log odds, I will change the S-shaped curve that ranges from 0% to 100%, yeah, just to a line. It's just a straight, simple line that ranges from minus to plus infinity. Isn't that kind of cool and nice? So if I illustrate this here with a couple of illustrations, if I take the proportion of a new form, I end up with this S-shaped curve, the logistic function. But if I express exactly the same change in terms of log odds, I simply get a line out of it. I simply express the rate of change, the speed of the change, the effect of time on a line. If you just type in a most statistical algorithm like log, it'll interpret it as the natural log. Otherwise, you'd specify log 10. Doesn't matter. What's important is the S-shaped curve expresses probabilities. That's nice and visual and a great graph, but it's very difficult to say how fast the change is because it's an S-shaped curve. On a log odds scale, the graph isn't as nice, harder to interpret, but the interpretation of the change is just linear and therefore much, much easier. So the output you get out of your statistics program is on this scale here. It's on the logit scale. So these A and B values that you get out must be interpreted in terms of log odds. So this B here in A plus BX That's once again our rate of change or the coefficient of time or the time parameter or the effect of year or whatever you want to call this. A large B means this line here is very steep. It's a fast change. A small b means this line is very flat. It's a slow change or no change at all. Okay. And then once again, the A simply moves this line along the x-axis. So that's less important for us. Okay, so this B here, this rate of change parameter is what you need to be able to interpret. And once again, we do this 2 or 3 times and it becomes very intuitive, very easy. Everybody can understand this. So you would have to say something like this. B, this rate of change parameter, indicates a change in the log odds of the new form for every 1 unit year increase in time. So if you go from 1450 to 1451, there's an increase in the new form by that many log odds. If you go from 1452 to 1453, there's again the same increase because this increase here is just linear, right? So from 1500 to 1501, from 1501 to 1502, from 1502 to 1503, every 1 year unit increase in time will increase the probability of the new form by that much, by the value of B in terms of log odds, by that many log odds. So for instance, you would say the rate of change indicates that the new form increases by 0.3 log odds per year, or 0.3 log odds for every additional year that passes, or something like this. So this is what you would have to describe in your paper once you interpret the results. Yes?
So once we write our paper, we only have one graph now. Do you still want us to both graphs, like put both graphs into?
I like the S-shaped graph much more, don't you? Just looks so much more intuitive. I mean, if you want, we will talk about the visualization, but I think we want to create a graph like this. I mean, it's very easy to do. If you think I actually prefer that graph, if you could. I find the S-shaped graph nicer, more intuitive. Because who thinks in log odds? But people commonly think in percentages. Okay. So here's an example. Logistic regression might return these results with the A value minus 31 and here 0.058. Could anybody formulate, give a nice formulation of what B means if you had to write a paper? Okay, yeah, the idea is correct. Here is maybe a formulation. The new form increases by 0.0258 log odds per year for every 1 year increase in time. Do you like this formulation? Is that intuitive? It's not difficult, huh? Okay. So this is what this would look like on your logit scale. For every year you go on, right, from 1100 to 1101, or from 1253 to 1254, for every 1 year unit increase, since this is a line, the increase in terms of log odds will be the same. Then I can transform this back on a proportion scale, and I would sort of get this S-shaped curve here, right? So this log odd scale, that's a line. This S-shaped curve, that's for proportions, are the same thing, just different ways of expressing it. But here I can give an increase per year. Here, that's more difficult. So what I like to do for the S-shaped curve is to give how much time in years it takes for the proportion to rise from 1 to 99%. That's not really standardized. That's something I like to do because it's very intuitive. So if you have a rate of 0.0258, that corresponds exactly, it's exactly the same thing as saying it would take 356 years for the innovative form to go from 1 to 99%. Those two expressions are equivalent. They mean the same thing. So this rate of change parameter, 0.058, corresponds to a transitional period or a period from 1 to 99% of 356 years. Does that make sense? And in the next session, I'll tell you how to calculate this time span from 1 to 99%. Not today, next time. This is something you need to hear twice, I think, to really intuit it. But luckily, we have 3 sessions, so it should be super easy and intuitive once it's all said and done. But if you have any questions, again, now, that would be, let me know now. You still with me? It's not hard, right? So far, so good. So what I thought I'd do, because I can't now give you a week time to review this, I just review it again. So I'll tell you the same thing in some sort of summary. Okay, let's see if that makes sense to you. We create a data set. It has linguistic variation in it. For instance, dative experiences versus nominative experiences, or eth versus s, or do support versus no do support, or be versus have, and so on. And also crucially time. Time is the one variable to focus on today. And we make a graph, a data cloud, where x is time and y is a proportion of the new form from 0 to 1, like this, with those yellow dots. What we want to do in logistic regression is fit an S-shaped curve through this, the best sort of S-shaped curve that describes this data. So put a line through it like this, right? In order to do this, we use logistic function and we get, or logistic regression, we get out of this two parameters, A and B. B is the important one. B is the rate of change parameter, the coefficient of time. And it tells you how fast the change happens. You interpret this B on the scale of log odds. It tells you how fast the change happens in terms of log odds per year, increase in the log odds of the new form per year. Also, another way of interpreting the same thing is how long does it take for a change to rise from 1 to 99%? Those two, the log odds per year and 1 to 99% are equivalent. They give you the same result just from different perspectives. So for instance, if you get a year parameter of 0.0318, in your paper, you would have to write something like, the new form increases by 0.0318 log odds per year. Can I see some nodding? Does it make sense? You all get this? Cool. Then let's continue and try to do this in R. So you should all have installed R. Let me see if I have R here. Yes. Let me see if I can share the screen for people on Zoom. How do I do this? Zoom. Here. Okay, so the first thing you want to do is take your data set from Excel and copy and paste in only the relevant variables, because oftentimes in the examples you have special characters, especially in Middle English. The data set is very, very large, includes all kinds of variables you don't need. So my recommendation is just take the Excel data set, highlight and copy the relevant bits, and put it into a much simpler data set like a TXT file. That's so much easier for Excel to run. It's a much smaller file. You don't have to do this, but that's what I would do. Okay, so first step is get the data set that you can put into R and make it as simple as possible so that you don't get any error messages. Okay, so I have created a data set here that we worked on with a previous cohort of students, and that is about the development of help to do something to help do something, the omission of the non-finite marker to after help. Okay, so you can either do help to do something, in which case the data set codes the to variable as yes, there is a to, okay? Or you can leave out the to, and then the data set codes this as no, there is no to. This is illustrated here in examples 1, 2, 3, and 4. A little piece of the lung does no harm and may help to fix the color. That's from 1829. Come help us to cultivate them. That's from 1800, okay? In modern English, you're much more likely to say something like in 3. A useful tool that, if successful, would help guide millions of young people through their first big life decision, from 2016. And note there's no to here. Or it will help us understand the concept of transience. Again, that's from 1970, and again, no to here. Also, the data set records the gender of the author, male or female. So with this data set, we wanted to see if female authors are more advanced in their omission of to than male authors. Different research questions, still interesting, but you get the data, right? Okay, in order to load this into R, I would like you to use this command here, read.table. So all you need to type in. If you have your computer here, you can try this out. The help data set is on Blackboard. Phi.choose, open brackets, comma, header equals true, comma, set equals, then inverted commas, /t. Just type all of this in. What will happen is that a little window opens up. Let me see if I can illustrate this. just put that here in R. Let me see. Yeah, you should be able to see this on Zoom, but okay. Press enter and a little window should pop up, maybe. Hello. Here we go. And then you just navigate to wherever you stored your file. I just put the folder on my desktop. What do I call it? Help something. Here, help dataset. And now I have stored the help dataset in what I call here data. Yeah, you can call this data anything you want, X, data 2, my data, whatever. What you can do is just type in data and it will output exactly what you put in there, data, enter. And here you see the entire data set. So there are 2,083 rows. Some of them are yes, some of them are no. So that indicates if the to infinitive is present or not, a year variable. So that's the date of the text, a gender variable, male or female, and then the title of the text. It's very, very similar for us. We are going to have a variable here, dative or nominative experiencer, a year for our text, 1400, 1450, 1500, 1600. We are going to have an audience variable, learner texts versus lay people text, and also the actual title of the text, the shortcut of the text. Yeah, does that make sense? Another thing that you should know is the abbreviation STR, which stands for structure. And then you can also do structure, open brackets of your data. And that will give you some information on your data set. So here it tells you there are 2,083 observations. Hopefully we'll have a lot more than 2,083. This is the variable 2, the linguistic variable. Either 2 is present or it is not present. Help to do something or help do something. The year variable, the gender variable, the title variable. So this is also a useful summary of the data, right? That's all you need to know. You have this actual data, just type in data, you see the entire data, or type in structure of the data, STR of data, and you see this nice little convenient summary. That isn't too much, right? That's easy. Okay, so the next thing is actually running the regression. There are many different ways of doing this. One simple way of doing it is like this. GLM, that stands for generalized linear model, GLM, and then open brackets. And in those brackets, you first have your linguistic variable. In this case, it's 2. For us, it's going to be the form of the experiencer, or whatever you want to call it. Then this little squiggly line, the tilde, you have to find where that is on your computer. And then the here. What that means is put on the y-axis the linguistic variable 2, and put on the x-axis year. That's the dependent variable, that's the independent variable. Then you specify your data, so data equals, and then this variable here needs to be whatever you called your data set. The last parameter you need to specify is family equals binomial. Okay, so let's do this. Let me just copy this. Here, put it into R. If you run into problems, and you probably will of any sorts like this, always just contact me and we'll find a solution. I've always found a solution for problems with students. Nothing's ever been terminal. But yeah, okay. So anyway, I ran this command here. Logreg is the name I gave to my logistic regression model. Okay. And now this contains all the information from this model. I can just type it in. So log.reg for logistic regression, and it outputs this. Here you see intercept. That is your parameter A. And here you say year, in this case, minus 0.01723, and that is the parameter B. That is the importance of the year variable, the rate of change, the effect size of time. Does that make sense? So we find an effect of time of minus 0.01723, formulate what that means. So maybe you can all just think about it in your head real quick. This is what you might write in our final paper then. So it tells you how fast the 2 is disappearing. And help to do something becomes help do something. Help me to understand logistic regression is becoming help me understand logistic regression. So it tells you how fast this is disappearing. How fast is the 2 disappearing? Okay, so for every 1 year advance in time, the log odds of finding the non-finite marker 2 decline by 0.01723. Isn't that a nice formulation? Isabella, do you like this formulation? All right, okay. Okay, does it make sense? Here I create a graph. Here's the x-axis. It goes from 1780 to 2016. Every dot here is a text. So there are lots of texts, 199 texts. You can see it's all over the place, but you can clearly see a decrease in the presence of 2, right? And then this red line here, that's the model. And the slope of this model, the decline, is minus 0.01723. So that's how you would interpret this. That's what the B means. It's the speed of this change. You cannot the logouts go from infinity to minus infinity. There is logically no real start or end point in logistic regression. There's always an infinitesimally tiny small chance of finding the innovative or conservative form. It is never quite 0. It is really, really tiny and really close to 0, but it won't ever be really, truly 0. But I'm not a mathematician, so I don't actually know if, I don't know. This is how I understand it. This is how it makes sense to me. Hopefully it'll make sense to you as well. Okay, so this is all we have time for today. For next time, after the Easter break, you need to finish the data collection. Remember, it's due by April 27th. I hope you all arranged a little study group with other people. Did you manage to do this? Ideally, you have finished the like verb already. And then if you have any questions about need or rule or whatever, just send me an email and I will try to provide some feedback. I mean, nobody's done this before, so we don't really know what difficulties to expect. But then when we meet again this week, we will take the data and live, bam, show the graph and see if we actually find something interesting. So it'll be very exciting. So hopefully you take this task seriously and try to do the data collection and correction with as high a quality as possible. But in the meantime, enjoy your Easter break. Thank you very much for coming. Relax, have some fun, but also work on historical syntax. And if you can, please go through these slides again. They are on Blackboard. There's also this how to do data set. And just type in these 2 commands. Type in read the table to put the data into R, and then run a logistic regression to get these 2 numbers A and B, just so you've practiced this once. Okay, so before we meet again next time, please go through these slides again as a refresher. Are we all good? All right, great. So enjoy, have a great Easter break, and I'll see you next time.